All right, so I've already introduced myself at least once, so I'll skip that part, sort of. I'm a senior solution architect at NVIDIA, and I'm going to be talking with you guys today about some of the projects in deep learning in climate, weather, space weather that I've been working with various groups at the national labs and universities. So we've seen so far that artificial intelligence can do some really exciting and impressive things. Some of the things you may have seen in the news include the ability to defeat world chess champions and Go playing champions and other strategy games, which are really pretty impressive. It can operate vehicles autonomously. Pretty soon AI will be driving your car as well or better than you, and by pretty soon we can speculate on the time frame on that. You can communicate natural language with your devices, Alexa, Google Now, things like that. You talk to it, ask it a question, it looks up the answer and tells you back in speech what the answer is. I use this all the time in my house now, and I'm teaching my 4-year-old daughter to do so as well. She thinks it's normal. And you can generate original content. You can generate stuff that simply doesn't exist. All the pictures of people you see in this image don't exist. These are generated faces. There's a website called This Person Does Not Exist. You can look at and it'll give you a face of a person that doesn't exist. You can generate videos of things that didn't happen, and pretty soon they're going to be indistinguishable from real ones. You can generate full musical scores. If you give the latest natural language processing models 2 sentences, it'll generate the rest of the article for you, and it'll fool at least half the people. So you can do a lot of really impressive things, some of them good, some of them maybe not good. So all of these things were accomplished with 2 techniques. All the ones I just showed were accomplished with either deep supervised learning or deep reinforcement learning, which is kind of a variant on it with trial and error added on. But most of them were done with deep supervised learning, which is really nothing more complicated than you give it a set of inputs and a set of outputs, and then you ask deep learning to connect the dots in between. So inputs to outputs, connecting the dots, that sounds like you found a function that sounds like curve fitting, right? Because it is curve fitting. That's exactly what deep learning is. So here's what curve fitting looks like in low dimensions. So let's see if the movie works. Yep, so I drew some dots on the screen, and I'm fitting a Taylor series, polynomial to this thing. I'm using a minimization scheme. Let's see if I can run that again because it was super fast. It finds all the right parameters to fit your model, and there you go. I fit a curve to the points, and now I can predict the value of new points. 1 point in, 1 point out, traditional curve fitting. Deep supervised learning is nothing more complicated than this, except that we're doing curve fitting in very, very high dimensional spaces. So the inputs maybe are images or sounds or 3-dimensional or 4-dimensional model fields. Like the things on the left. The outputs could be anything. They can be numbers, they can be other images, they can be sounds. So you're just fitting a curve from high dimensional inputs to high dimensional outputs. And instead of 4 or 5 Taylor series coefficients in between, you probably have 100,000 or 1 million parameters. So it's just curve fitting, but really big curve fitting. I think the best way to think of supervised deep learning and these curve fitting techniques as a new tool for software development. So here I have an example of a piece of software. You're taking in temperature, pressure, and moisture, and maybe you're outputting the probability of rain in your location. All software is a bunch of functions that take in values and output other values. Inputs, outputs, so you've got functions just like in the last frame. The way you do it right now is you logically think about how you would break down this function into pieces, update my mass, momentum, energy, macrophysics, microphysics, and you break those down until you have an algorithm that takes you from one end to the other. You need to connect the dots. Deep learning also connects the dots, but it does it with an equation. You put an equation in there with some unknown parameters, and then you reverse engineer that equation from data, lots and lots of data that adjusts the weights and the biases until you map your inputs to outputs in a way that matches your data well. So it's just another way of making these functions, but reverse engineering it from data rather than forward engineering it from your logical understanding of the world. This can be just as powerful as the other way, and in some cases much more powerful, because it can create pieces of software that maybe you could not have created yourself. One of the really great things about doing it this way is any function that you've learned through deep learning is automatically optimized to run on your accelerator, on your GPU. So you've got some data that came from your model, and it finds a function, and this function will automatically run in optimized fashion because it's composed of nothing but a bunch of matrix multiplications and nonlinear operations that can be done in a massively parallel fashion. These simple operations have been optimized, and wow, look, you suddenly have a piece of code that's been ported onto your GPU without a year's worth of effort. So this is kind of, if you can do it this way, it's a substitute for porting and a great way to utilize your GPUs. So there are a lot of ways to use your GPUs, and I am not trying to disparage the other approaches. You can drop in libraries, you can do OpenACC directives, you can write it at the CUDA level, you can use NVIDIA's Rapids ML tool, but in my opinion, deep learning is one of the most interesting and exciting ways because it allows you to utilize your GPUs and to do things that you just couldn't do with any of these other techniques. So we can use this new set of tools, this optimized software learning trick, to enhance all of our existing applications. Everything you do with software, you can now do with software possibly better. So here, looking at the numerical weather prediction pipeline, we can improve our data thinning, assimilation. You can possibly improve your dynamics. You can definitely improve your physical parameterizations, the way you communicate the data, the way you sort the data. You can also use it to build things that you simply couldn't do in the past. So that's still an open frontier. Some of the ideas that I think are pretty cool are real-time weather prediction detection on a global level. So you take your satellite data and you automatically detect all the interesting things that's streaming off your satellite. It takes microseconds to do it. You can look at all of your data. Environmental modeling, monitoring for change. You can use the strategy learning that they use to defeat Go players to figure out the best way to evacuate a city or prepare a city for a disaster. You can search the skies for every near-Earth object. You can accelerate your data assimilation. You can train your drones to run autonomously. When you're not able to communicate with your Mars rover, it can think to some degree on its own of what it should do next. You can enhance and repair your data. You can build better parameterizations. So I'm going to run through some examples of projects I've worked on. Notably absent are dynamics and physics, which are often covered by other people. So I'm going to start with some feature detection examples. So working with the NOAA Esrael group, Mark's group, we've done some real-time weather detection type things working towards this goal of detecting really important events in our satellite images. Some of the features we might like to detect are tropical cyclones, extratropical cyclones, convection initiation of wildfires. These are ones we've worked on. Other ones may be atmospheric rivers, storm fronts, tornadoes, cyclogenesis, blocking highs, volcanic eruptions, tsunamis. You can detect all these things automatically using deep learning because you can detect them yourself and train a neural network to do it as well. So you can detect them by building a large data set. You can build a tropical storm data set using the IBTrax database, which is a database of labeled tropical storms. This gives you your positive and negative examples, and then you can use that to train your deep learning neural network model. Usually you use a convolutional neural network to do computer vision type tasks. Here's the model that we've been using. It's called a UNet. It's just a bunch of convolutions and down pooling operations. That allows you to detect features at multiple spatial scales. I use this UNet and variants of it all the time. It's a really very powerful tool. And on the right are the labels that we gave it and the target segmentation. Basically, we asked it just to put a square at the center of any tropical storm. So you input water vapor, you output pixels saying, is this a tropical storm? And here's a result of a model I trained myself. So here you have the water vapor field, and you're outputting the predictions. The predictions are the little red squares. The ground truth are the little blue squares, which are underneath the red squares. And most of the time, you can't even see them because they're right on top of each other. And what that means is we've gotten the right answer. We didn't ask it to output squares specifically. We just said, this is the segmentation you should give us. And when you've trained your network really, really well and accurately, it gives you back what you told it to look for. So what's really exciting about this is that although it took creating the training data took lots of fields. You had to have temperature, pressure, wind speeds, expert opinions to generate those labels. Now all we need to detect tropical storms is this one single field, water vapor. I input a water vapor field and it'll tell me if there's a tropical storm in the picture. And it does it instantly. So it's really fast and it uses a lot less data, and you don't need a full data assimilation or a weather model behind it to do this. So building on that, the Esrael team said, well, we only need the water vapor field, so that means that we can do detections directly from satellite images. So here you see the satellite images coming off of GOES, upper tropospheric water vapor band, I believe. The ground truth is the little red labels at the top, the little red squares, and the bottom is the segmentation of the model they trained. And here you can see that they're getting the right answer, and you didn't need any of those other fields to do it. You just were able to train it on the same results to give you answers directly from water vapor field. Another project that they're working on is they're predicting convection initiation directly from GOES observation. So again, directly from satellites. In this case, the ground truth labels were derived from radar reflectivity. So if you have composite radar reflectivity with decibel Z greater than 35, Then you label that as convection initiation event, and the ground truth is on the left, the prediction is on the right. And even though the prediction is a bit smoother, you can see that generally it's placing convection initiation events in the right places. So satellite input in, direct predictions out, fast and simple. So you can use the same approach, computer vision, UNet, detection technique, to detect lots of things. It doesn't have to be weather on the surface of the Earth. You can detect space weather, like interesting features on the surface of the sun. I'm working with NASA Goddard, Altamira, and ourselves in order to predict things on the surface of the sun. In this case, the data input is from the Solar Dynamics Observatory. It downloads 1.5 terabytes of data per day, which is far too much to look at in a traditional approach. And it has 10 wavelength channels, as you can see on the right here. And we want to predict lots of interesting features: coronal holes, active regions, sunspots. Eventually, we'd like to predict solar flares and coronal mass ejections, because those can have a large impact on life here on Earth, filaments, and other things. So I trained this model the same way, the exact same way. So here's a UNet model. The ground truth is the blue contour, which was created by a heuristic algorithm, which is very, very slow. They've only been able to label a few images this way. And the yellow is the prediction by the trained neural network trained on this same heuristic data. And so if you had a perfect answer, the yellow would completely fill the blue contour, meaning that it's fully confident of the right answers. And you can see that it's doing a fairly good job. It's not too bad at all. And again, we can predict now directly from this just one or two fields what the right answer is, and do it very quickly. So now we can look at all of the images that they've downloaded over the many, many years, go back and label all of them appropriately. If you want to go on and predict sunspots, you are getting into a very, very highly imbalanced data set, which our keynote speaker touched upon. Basically, sunspots are very small. So most of your image, 4K by 4K on a size per image, almost all of them are zeros. It says there's nothing here of any interest. And if you try and fit a machine learning or deep learning model to this naively, it'll say, you know, I can do a really good prediction by just saying there's nothing here. All zeros. I'm very happy. 99.9% accurate. You don't have anything of any interest. So yeah, it's great. It's like, okay, I did a good job. So in order to get around this, you have to create a balanced data set somehow, or use a specialized loss function. So one way is to use the focal loss, which focuses in on the interesting stuff and ignores the stuff that's easy to predict. Another way, which is the way that I usually use, is to create a balanced data set. I look for positive examples, sunspots, and I balance it with negative examples. And then when I'm training my model, I shuffle them together so you have 50-50 of each. So every time it sees one sunspot, one not a sunspot. And therefore, you're never too imbalanced in terms of pixels, and it never gives you back a result with all zeros. So when you train a model this way, here we have the output of this model on data that it hasn't seen before. The ground truth, again, is blue. The correct answers are in yellow, and you can see that the yellow is exactly within the blue. Basically, we nailed this, and we get every single sunspot exactly where it's supposed to be. So we're happy with that result. Here's another example of the same technique applied to a completely different feature, active regions. I took the same model, gave it different data, and essentially created a different piece of software that detects a different thing. If you were to do this by hand, you'd have to start from scratch and say, how do I detect an active region? What's its magnetic characteristic? What do I do to detect this? So this is a really powerful approach, this deep learning approach, and I suggest everyone learn to use it. Some other things outside of feature detection, you can use generative models. For example, you can use GANs to accelerate your data assimilation process. Basically, what you do in data assimilation is you have some satellite radiances and you want to predict some model variables and integrate them into it. Or you can do the inverse, take your model variables, use a forward model to predict your satellite radiances. You can use a deep learning neural network to do this. This is what you get at the bottom middle. If in an intentionally difficult problem, I gave it only upper tropospheric water vapor and asked it to give me back the model's prediction for total column water vapor. And what I get in the lower middle is the prediction. And it should look fuzzy to you and make you want to pull out your glasses if you have them. As Matt Norman calls it, the bottom result is gooey, and the result that we want is crispy. Is that what you said? Yeah. So what we want is a crispy result, and you can get a crispy result by using a generative adversarial network, which is basically a standard, what do you call it? I don't know. Let's just call it a data structure in a deep learning framework, where you have two models compete, and what you end up doing is training a neural network to randomly select one state from the distribution of possible states by putting in a random number and training it to specifically learn the distribution of states. So that's what I have on the top here. The same input on the right is a target output, what the actual answer is in this case. And in the middle, I have one of the generated results, which for most people, they wouldn't be able to tell which of the two was real. So basically what you're doing is predicting one member of your ensemble rather than the ensemble mean. So in many cases, in like physical parameterizations, for example, this is what you want. You don't want the fuzzy mean. You want one instance of the set. So it can be very hard to train generative adversarial networks, which discourages people from using them. I have a trick called Regressive Gann. What you do is you train just the regression portion first, you get near the mean state, and then you turn on the Gann loss, and it allows you to spread out from that mean state until you capture all the distribution dynamics. And this tends to work very, very well for conditional generative adversarial networks, where you have something to condition upon. And apparently this technique is not widely known, so I seem to need to publish a paper or something. People who use it seem to be very happy with it. It helps them out a lot. So if you're having trouble with your GANs, try this. I worked with Tianlei Yuan at NASA Goddard and his coworkers. They're doing a project with conditional GANs on cloud generation. So they take very small patches, sea surface temperature, things like that, and use it to predict what kinds of clouds are going to be there and what those cloud patterns will look like. Then they applied that to the entire globe, which is on the left, the correct answer is on the right. And generally they're getting the right cloud densities and types, although they're missing some of the larger swirling patterns because they're looking at very small areas. But it's a very promising result and something that they can build upon. Another thing you can do is enhance your data. So satellite and model data both. Some of this is done with the Free Universität Berlin. So NVIDIA has a super slow motion technique that you may or may not have seen online. Basically, you input a normal video from your camera, which is in the top, and it generates the video on the bottom. It looks like a high-speed, 240 frames per second video that you may have taken with your camera if you had thought to do it, but you didn't. But actually, all those frames are interpolated and generated, except for a few of them. So I thought this is a really cool thing. I really love watching these videos and trying to see if I can even figure out if it's real or not. And maybe we can apply that to something else. So I decided to try to apply it to interpolate satellite loops. So you can use deep learning to predict the optical flow, and then using the optical flow, you can advect the image, which is what I did. And here's the result of that. So in the lower left, I input 10 frames from a GOES 15 water vapor band, and in the upper right, I'll put 110 interpolated frames, just using advection, using the optical flow that's been predicted, and it does a pretty good job. You can really build upon this and get a much more accurate result than what I'm showing here. But you can see the potential of this to basically create intelligent interpolations of your data, which has a lot of potential uses, which I don't have time to go into. Another thing you can do is data inpainting. This is another NVIDIA application. So here someone is intentionally damaging a picture they took. They're erasing rocks, they're erasing sticks, and then they're asking the inpainting algorithm to fill in the remaining pixels with what probably should have been there and what they would actually rather see there. So they're taking out all the ugly things and making a pretty picture. You can take out bridges, you can take out people. And this is accomplished with the same basic network I showed you before, adding something called partial convolutions into it, which I don't have time to go into, but basically it masks out the data that it doesn't like and uses the rest of the data. You can use inpainting to do amazing things in climate and weather, and here's a result that we've just submitted from Christopher Kadau at Free Universität Berlin. And what he did is he's using it to fill in missing HADCRUT-4 data, so missing climate observational data. HADCRUT-4 is very incomplete. You only have a few values and lots of missing data values, and he wants a complete gridded data set. So what he did was he trained a neural network on some climate model data, which is complete, verified that it's able to predict itself correctly, and then used transfer learning to use those inputs to predict what outputs would have come from these observations. And then he held out some of the observations themselves to check that that was also working correctly. And this works amazingly well. He's able to basically correct the observational data set, all the way back to 1850 or whatever. And he's used it to update how much warming we've gotten. And I was impressed with this paper. So another thing you can do is you can fill in missing data in the GOES 17 observations. The GOES 17 satellite has a cooling problem. There's a blockage in its cooling structure. So at certain times around the sun, it overheats and it drops out a lot of data, and all you get are those little stripes worth of data, and you basically have to throw away those frames. But you can actually fill in the missing pixels in these frames if you have some of the some of the channels are remaining. There's redundant information there which can fill in the broken channels. Sometimes you're missing all the channels, but you have little bits of data in each of the channel. And that you can condition upon to guess what the most likely values should have been in between. So you can turn that damaged data into usable data using the same in-painting, in-filling technique, which is what he's showing here. So the last example is a time series prediction, which I haven't done as much of. This is a project with UC Davis. They're trying to predict stream flow under climate change scenarios. So in the future, they've got the climate change models, and it tells you how much rain is coming in. But they would like to predict how much stream flow you get from that. You can run a separate model to model the stream flow, or you can train a deep learning neural network to basically try to predict how much stream flow you get. So we input the time series of the precipitation. We output a different time series, which is the stream flow. And it's able to do as good of a job as the procedural models at a much, much smaller fraction of the time, like 10,000 times as fast or better. And we're able to get a really high correlation of everything except the super big floods, which is going to be a separate stage of the research if I ever get around to it. So basically I have to do extreme value detection, which will take a bit of a different setup. All right, so anyway, let me summarize the important points since I talked about a whole lot of things, mostly results. The points I want you to take away is that supervised deep learning is very powerful, but it's not mysterious. It is curve fitting. You should think of it as curve fitting, but curve fitting in very high dimensional spaces. So it's not mysterious. Don't be scared of it. Just use it. It's a different way to build software. Curve fitting and software reverse engineering are the same thing. You just reverse engineer from your data. It is a really great way to take advantage of your GPUs. Yes, you can port the models that you have, but to some degree, you're probably better off building a new model directly from data. It will automatically run on your GPU, take advantage of your GPU, go super fast. You can do really amazing things with this, like I showed in the first few frames, things that can't be done in any other way because it's a new set of tools that hasn't been available before, or it was available, but it wasn't fast enough. And I think it's just going to become a standard part of the numerical weather prediction climate modeling toolbox, and the faster we pick it up, the better. So if you have any specific questions or would like to collaborate with me, my email is dhall@nvidia.com. Thanks for your attention.